Here's the bell work. Hopefully you guys got that done by now. You're supposed to have it done by the bell, you know. Alright, so there you go. Got 9/20ths on number 25, and 26 gives you 1/6. So here's our objective for today. I can simplify expressions by combining like terms and distribution. We're also going to do the inverse of distribution, which is called factoring. We'll go over that pretty quickly though, so copy this down. Alright, here's some very important vocabulary terms that we need to understand, like what is the difference between an expression and an equation. Well, an expression doesn't have equal signs where an equation does. So an equation actually is where we have two expressions that are equal. And in order for something to be considered a math expression, it only needs what we call a term, one term. Sometimes it's just a number, sometimes it's a number with a letter, sometimes it's just a letter, you just never know. But they can be quite long as well. So what is a term? A term is a value in a math expression separated by addition and subtraction, but it takes the operation to its left as its sign. So a constant is just a regular number. Sometimes you add that number, sometimes you subtract it. If you subtracted it though, you'd consider it a negative. And then a coefficient is a number being multiplied by a letter. So in not so technical terms, this is some decent sentences for these. Now just remember on this, a term will always take the operation as addition or subtraction as its sign, right? So if it was subtraction, we consider it negative. Now what this also means is that if you see division or multiplication, which also includes distribution, then that is not considered a separate term. A term can have lots of multiplication or division in it, but it would still be considered only one term. Now while you guys finish writing those down, just look at maybe some examples of this, right? An expression and an equation. Sometimes an expression just has a number in it, maybe like 4 or something like that. Sometimes it can even be x minus 4. Sometimes it can have exponents, you just never know. But that's what an expression can look like. Sometimes it's just an individual value, but the moment you put an equal sign into it, then you have two separate expressions that are being compared, such as sometimes you have different letters, sometimes you have more numbers, you just never know, okay? But the moment you put an equal sign into it, then it's considered an equation. Now, from this example even, we could say that equation has how many terms? Well, you'd have one here, there's one, there's one, and there's one. So that one would have 4 terms because they're separated by, like this one, subtraction and addition. Maybe we should have put an equal sign in there as well. But when we look at terms, we're looking specifically at expressions. So it'd say this expression has 2 terms and this one has 2 terms. And then constants, again, they're just numbers. Like in this expression that we have up here, -4 would be considered a constant. Now, why is it -4 even though it's showing subtract 4? It's because a constant, or any term actually, will take the operation to its left as its sign. And same with this one. This is 5, but again, this is +5 because it's showing as addition. And then coefficients on this one, that's numbers being multiplied by letters. We'll talk about that on the next slide. Alright, so let's complete this table. We got 3 different expressions. We're going to identify the terms, the constants, and the coefficients for each of these. Alright, and then later on we may even talk about like terms. Well, not on this, doesn't look like. Maybe there's a couple. Whatever. So we got expressions, and this first expression here, 4x to the power of 2 minus 5x plus 2y minus 3, that has a total of 4 terms, because again, even though it's 4 times x to the power of 2, it's still considered only one term. And this will be, that idea of knowing what a term is will be pretty crucial once you guys take calculus. It's still pretty crucial right now, but in a slightly different way. So the first term I see on this one is, well, 4x to the power of 2. Alright, so that's my first term. I'm going to separate it with a comma right there. And then the next term, it's not just 5x, you guys, it's -5x right there. And then the next term is 2 times y. And again, we just write that as 2y. And then that last term, again, it takes that operation to its left, subtraction as its sign, so it's considered a -3. Now the constants that I see in this one, there's only one term that does not have an x or a y, and that's, well, -3. Yeah, the 2y and the 4x to the power of 2, we don't write those with the positive signs because math people are lazy, so we don't actually write those signs in there like that. Once we see that, like, we got these four terms, right? 4x to the power of 2 and -5x and 2y and -3, you could rearrange that expression in any way that you'd like without changing its value, as long as you know the value of each term. So you could have written that, for example, as 2y plus 4x to the power of 2 minus 3 minus 5x. And that really is the commutative property of addition, because instead of writing these as subtraction, you could say you're adding negatives to those. So coefficients on this one, they're just numbers being multiplied by letters, such as the first one is 4. The next one I see is being multiplied by letter is -5. And then the last one I see being multiplied by letters 2. Now, you could say specific coefficients, like what's the coefficient of x? And you'd say -5. Or you could say what's the coefficient of y? And you could say 2. So these are all coefficients, they're just coefficients of different variables. So now that we have that one, let's go to this next expression. So we got 7 minus a plus 6a, well, 6 times a times b times c, plus a minus 4. And what is that? 1, 2, 3, 4, 5 terms on that one. Okay, so let's list them all. I got a 7, and again, that's a -a. And then there's a 6 times a times b times c. And then there's a positive a, and also a -4. Okay? Well, it tells us to find the constants. So let's list all the constants. Again, these are numbers without letters. There's just 7 and also -4. Those are constants. Now, just so we understand, and this is coming very soon, but these are like terms. They're two constants, which means we could also combine them to simplify this expression. Now, the last thing it wants here is coefficients. And the first one we'd want to see is this one right here, right? That's a -a. Now, we should ask ourselves, what number is being multiplied by that a? And hopefully we know that that is a -1. Now, that's a phantom one. It's not being shown. It's there, though, that phantom one. Which is why these phantom numbers are kind of creepy, right? They're there, they're watching. They're always watching, always lurking in the shadows. So, like this one, this next a right there, there's a phantom one right there. So you could say, you know what, there's another one. Phantom one right there, okay? And we need to identify that so that we know what is actually being multiplied by that letter. And that'll be crucial in various situations. The next coefficient I see, now there's a 6 being multiplied by an a, b, and c on that one, but the coefficient is just an individual 6 on that, okay? So 6 is its own coefficient. And a, b, and c would be considered variables on that one. So coefficients can also be fractions, but of course, just to kind of simplify it for now, we're looking at integer values. This next expression, we got m plus n minus p plus q. So, well, that's 4 different terms right there. You got an m, an n. Now that's a -p, and if you would like to show that phantom 1, you're welcome to do that. And then finally a q on this next one, okay? In fact, I showed that -1. You could show a phantom 1 on the m, n, and q as well. Just positive 1, that's all. So what are the constants on this one? I don't see any constants. There's no numbers by themselves, okay? But I do see coefficients. The coefficient of m is that phantom 1. The coefficient of n, also a phantom 1. The coefficient of p is a -1. And the coefficient of q, positive 1. Now, it's pretty crucial that you guys understand these 3 vocabulary words, because I'm going to be using them, well, 4 actually, with expressions. We're going to be using these pretty much all throughout this unit and for the rest of the year. So when I say terms, we need to know what you guys mean. We need to know that you know what I mean. Or if I say constants or coefficients or expressions. Okay, you need to know what we mean by that without having to continually translate that for you. Okay. So imagine you have a box of donuts. Oh, I can do that. You can see how many donuts are in the box. So you use, oh sorry, you can't see how many donuts are in the box. So you use the variable x to represent how many donuts there are inside the box. Assume every box of donuts has the same number of donuts inside. So this is related to what we talked about last time with symbols, is you can use symbols to represent various things, and since we don't know how many donuts are in the box, we can use x. So this says, write an expression to represent 13 boxes of donuts, and yeah, we do get to assume that each box has the same number of donuts. And I would really hope that there's 12 in the box, you know.
I would hope there was going to be a baker's dozen.
But yes, well, I would actually hope that there's, you know, like 100 in the box. You know what I'm saying? I like the chocolate covered one. Anyways, that's a whole different matter right there, right? So it's a, well, we know that the number of donuts inside a box is x. And, you know, we wrote expressions like this last time. But in this case, it says that there's 13 boxes of donuts. So multiply that by 13. And again, whether you show the multiplication there or not is really up to you. It is not required, though. And in the future, I'm just going to write it like this. And that would be read as 13x, where we know already that x is the number of donuts inside every box. So every box has the same number of donuts. Hopefully, you know, like 100 and more. All right, write an expression to represent 9 boxes of donuts and 4 loose donuts. All right, you guys take 30 seconds to do that. 30 seconds, go. All right, let's see how you guys did. So the first thing I'm going to start with on this one, and you wouldn't have to start. You could start with the 4 loose donuts if you'd like. But I'm going to say, you know what, I got 9 boxes of donuts, right? And we know x is the number of donuts inside each box. So multiply that by old 9er right there, the 9, because there's 9 boxes. Now that 4 loose donuts right there, they wouldn't be loose for long, but they are in this situation, right? You got 4 donuts that are extra, so we're just going to add 4 to that. So the 4 is the constant, and then we have a 9 coefficient of x on this one. But this expression would represent 9 boxes of donuts with 4 loose donuts. So if we knew how many donuts were in a box, we could actually solve this one if we wanted to. All right, imagine you have 3 boxes of donuts plus 7 loose donuts. Then you buy 2 more boxes of donuts and 6 more loose donuts. An expression to represent this situation might be this one. So yeah, they said you got the 3 boxes of loose donuts and 7 loose ones. I'm sorry, 7 boxes of donuts and 3 boxes of loose donuts and 7 loose ones. That's better. And then they also said 2 more boxes of donuts and 6 loose ones, right there like that, okay? Now, number 8 says, how many boxes and how many loose donuts are there altogether? Write an expression. Well, just in terms of boxes, right, we got the 3 boxes right there, and then these 2 boxes, which would combine to be 5 boxes. Well, it did say to write an expression on there, right? So I'm just going to write 5 times x, because x is the number of donuts in the box. And then also, you got the loose donuts, these 7 right here, and these 6 right there. So if we combine those, that'd give you another baker's dozen right there, okay? So this expression simplifies the original expression that they gave us. Now if you wrote that as 13 plus 5x, again, it doesn't matter. It still has the same value. It's just written a little different. We're not actually able to figure this one out because, and yes, I know most boxes of donuts come with 12, even though we would want more. But in this scenario, they said, well, let x be an unknown value. Maybe there's like a half dozen or 1 donut in the box. It's one of those real fancy ones, you know. All right. We can combine the 3x and the 2x to be 5x, which is what we did, because we're adding what we call identical or like terms, which in that case is boxes of donuts. But we can also add the loose donuts together, such as 7 and 6 to get 13, which is what we did. These are examples of like terms. So I'll use this phraseology also pretty often. Like terms. Okay, so if you haven't underlined that, I mean, I put it in caps, but I would probably underline that because I'm going to say it a lot. Like terms can be added together because their variables are identical. Or, like constants, their non-variables are identical. Combine the like terms in this expression. Okay. Well, let's take a closer look at this one. There we go. So we got two different types of terms on this one, even though there is 1, 2, 3, 4, 5, 6, 7, 8 different terms. 8 different terms, but 2 different types. Now, since there are 2 different types of terms in this problem, when we combine the like terms, there should be only 2 terms. Okay, so the first thing I usually do is look at the term farthest to the left, and this one has an x right there. It's a negative 2x. So I would scan this expression and look for any like terms with x's, such as this one. There's a 1x right there. And yes, I am showing that phantom one on purpose. And then this term has an x right there. And this one has an x. And yes, remember, they take the operations to its left as it's signed. So we got a negative 2x with a 1x and a 4x's and then a negative 2x's. So combining all of those x's, how many x's are remaining? 1x. Okay, negative 2 plus 1 plus 4 minus 2, bam, 1x. Now, a lot of people, especially when you become a lazy math person, you'll make that a phantom one, so you don't have to look at that garbage. Whether you think it's ugly or it's just too much work, maybe both. But yes, you can make it a phantom one, so you don't have to look at that garbage. Well, that's all the x terms. However, there's also constant terms, such as positive 4, negative 7, negative 3, and also positive 2. Well, if we combined all these, a negative 4 combined with a, positive 4, combined with a negative 7, combined with a negative 3, combined with a positive 2, gives us negative 4. Now, again, if you wanted to, you could have written it as negative 4 and positive x like this. It still doesn't matter, though, because the value of this expression does not change, because each term still holds the same value that it had before. Alright, now imagine you have some paper bags with chocolate candies inside. Oh, it's very nice. Each bag has the same number of candies, but you don't know how many are in each bag. So you use the variable y to represent the number of candies in each bag. How could you interpret the expression 2x plus 5y in context of the donuts and candies? Well, since x represents the number of donuts in a box, and as 2x, right, we could say we have 2 boxes of donuts, and that's the 2x. And then the plus sign, I would represent with the word and we know y is the bags of candy, or how many candies are in each bag. So I'd say the 5 of those y's tells us we got 5 bags of candy. Now you can specify, well, each bag and each box has the same number of candies and donuts respectively. But that's too much writing for me, and I am one of those lazy math people, so there you go. So there is an aspect of interpreting these, especially when you guys start looking at word problems like this. But when they have no context or word problems, then it really doesn't matter. All right, can you simplify this? Well, we would look at the 2 variables. Here's an x, and there is a y. So the real question here is, are there any like terms to combine? And in this case, since they are different letters, you cannot combine them. You couldn't say you have 2 boxes of donuts and 5 bags of candy, and therefore we have 7 bags of box candy donuts. I don't know how that would work. But that's why it doesn't work in math either. So number 12, simplify this expression by combining any like terms. Let's do it. All right, so again, this is just what I do. Not that you have to, but I start on the left. And I'm looking at y terms because this term has y. It's negative 4y. So I scan this from left to right, and so we got negative 1, positive 3x, positive 2, negative x, positive 3. And here's another term with a y, and negative 2y right there. And also the next term, that's a positive 1y right there. Those are all the terms that I see that have y's. So when I combine all of these, it should tell me how many y's I have. And negative 4 with a negative 2 and a positive 1 comes out to a negative 5 of these y's. Now my next term is a negative 1. That's a constant. So I'm looking for any other constants like positive 2, positive 3, and negative 5. And when I combine all of these like terms, let's see, negative 1 and a 5 and a negative 1. Again, right there. Okay? And you could put that in the calculator, by the way. -1 plus 2 plus 3 minus 5. And you should get -1 on that. The last type of term we have on this one is this positive 3x, all the x terms. Then we got a -1x. Well, these are easy to combine. Positive 3 with a -1 is a positive 2 of these x's. Okay, and there's different ways to write this. Right, if you said, hey, you know what, I want the positive 2 out, positive 2x in front, and then minus 5y, and then minus 1. It's the same thing. And yeah, there's more ways to write this, but that's good enough for now. Okay, but I just want you guys to know there's different ways to write it. And, well, there are formal ways to write it, but that's for a different class. Yeah, so I'll read that first one out. So this one, the first one reads -5y minus 1 plus 2x. Yeah. All right, here's these 4 problems. Let's just go over these very quickly, okay? So on number 13, that's not 13.8. That's just number 13. So again, we got all these coefficients of a's, right? And when we combine these, they're all like terms because they're all a terms. And how many of them do we got? Well, there's 1, 2, 3, 4 of them. So 4a is what this would combine into. Now 14, this one's a little different. Again, it may be helpful to see these phantom 1s and negative 1s. But when we combine all these, we are going to have some number of x's. But how many, right? Well, you got 1 minus 1 minus 1 minus 1. And essentially these two zero out. So we're just left with -2 of those x's. Well, what about these? Number 15. Well, you got some phantom 1s again. But these are all negative. So when we combine all of these x's, you got a bunch of negative x's. But how many? 1, 2, 3, 4. Bam. -4 x's. And then 16, again, we got some more phantom 1s. That's okay. But we have 2 different types of terms on this. We got the m's right there. And when I combine these, that would give me 2 m's. And then we also have these n's right there. So that's, how many n's is that? That's positive 2 of the n's. And again, if you wrote that as 2n plus 2m, that's okay. So if you were to purchase a combo meal at a fast food restaurant, you'd get a burger, a fries, and a drink. Oh, delicious. If you purchased 3 combo meals, how many burgers, fries, and drinks would you buy? Well, you'd since each combo meal comes with a burger, a fry, and a drink, you'd get 3 burgers. You'd get 3 fries.
You have 3 people.
And 3 drinks. Yeah, you guys are simplifying that already. Yeah, that works for me, right? Just make sure you define it, right? So you'd say B equals burgers on this one. Well, I'm sorry. It's just if you don't define them, then we get to define them, and then we have to mark it wrong, which we don't really want to do, right? So if you're going to use variables on this one, especially for word problems, right? You got to define what they are. So that's a drink right there. Now, just along these lines, because you guys brought it up, since we've defined these variables, let's write out the expression, right? You'd have 3 burgers, 3 fries, and 3 drinks. Or you could actually write this as 3 sets of burgers, fries, and drinks. So if you see what I got in parentheses right there in purple, that by itself is a combo meal, and multiplying that all of that by 3 in purple tells us it's 3 combo meals. Now that's a great point because this leads up to what we call factoring. So some of you guys notice that each of the terms in red, you got 3 B's, or 3 burgers, 3 fries, and 3 drinks. You can factor a 3 out of each of those, and I know I haven't defined factoring, but we'll get to it. You can do what we call factoring, a 3 out of each of these terms, which leaves you with just a burger, a fry, and a drink, which is just a combo meal. And then it allows you to write it in purple like this if that is what you would like, or if it's more convenient to write it like that. If you were to purchase a combo meal at fast food, you get the burger, fries, okay. Number 18, if you bought 7 combo meals, then gave away 2 of them, how many of each, I guess burgers, fries, and drinks would you have left? But let's show this using the expression, right? So B is burgers, F is fries, and D is for drinks. But we're going to buy 7 of those, right? 7 burgers, and 7 fries, and 7 drinks. But then it says we're going to give away 2 of these combo meals, right? So we're going to take away 2 burgers, 2 fries. I should give myself more space. 2 drinks as well, okay? Well, now we'd be looking to combine any like terms, like the burgers. 7 burgers minus 2 burgers is 5 burgers, not boogers. And you got 7 fries minus 2 fries, well, that'd be 5 sets of fries. And then 7 drinks minus 2 drinks would leave you 5 drinks. And again, since all of these have 5s in common, we could actually pull these out like this and make it 5 sets of burgers, fries, and drinks, which is a factored form of what we have in green. So 5 sets of combo meals. Yeah, so if you rearrange this, and that's a good question, like let's say, yeah, you wrote 7b minus 2b over here, yeah, that's fine. It still has the same value, it's just written in a different order. Yep, that's good. Let's look at this that way, okay? So yeah, you'd have 7 sets of combo meals, right? So that's a burger, a fry, and a drink. But we're going to give away 2 of these combo meals, so that'd be 2 sets of burgers, fries, and drinks. Okay? Now, what we had written in red and purple, there were 6 terms, but what we have written at the bottom here only has 2 terms, right? Separated by the subtraction in green. Now, what this means is that you got 2 like terms because you got BFDs. That's not a curse word, right? It's not okay. So you got burgers, fries, and drinks on this one. But you got 7 of them minus 2 of them, so that's 5 of them, right? And again, that's kind of the same thing we have from the factoring right there. Talk about this one. The combo meals can help you consider the distributive property when working with variables and expressions. If 3 variables are added together in a group, such as x plus y plus z, and 3 groups of them like this, then how many of each variable would you have? On this example, they've shown that 3 groups of x, y, and z. And, you know, would show this distribution with these rainbows, right? So that's 3 groups of x. And it's crucial to remember that the distributive property is multiplication. It's always multiplication. But that distributes the 3 into the x. It also distributes into the y, which is 3 groups of y's. And then also the final distribution right there, 3 groups of z. And again, when I say groups of, I'm talking about multiplication on that. Okay? So that would be the expression after the distribution. And we're going to see distribution quite a bit in this unit. I know there's one full lesson on distribution with equations, even though right now we're only dealing with expressions. Oh yeah, that would be like saying you got 3 burgers, 3 fries, and 3 drinks. So number 10, yeah, you could say whether you knew that this x was burgers, y was fries, and z was drinks, doesn't really matter, because you can use the distributive property to at least simplify this a little bit. So you'd have 7 groups of x there, which again in that problem was 7 burgers. You'd have 7 groups of y, and you'd have 7 groups of z after distributing the 7. Now this next one, this is a -2 term right there, which we are now distributing into this set of parentheses. Okay, so that's actually -2 groups of x, it's -2 groups of y, and -2 groups of z. And again, that would represent in the situation that you're giving away some kind of burgers, drinks, and fries, 2 meals, I guess. But then we can start combining any like terms like these x's right here. 7x's minus 2x's, that's 5x's, which would have been 5 burgers. And then you got 7y's and -2y's, which would combine into being positive 5y's. I think that was drinks. And then of course we got the z's, Same idea with that one, you'd have a positive 5z's, which I think was drinks in that problem. So we started with two terms with the 7 multiplied by x plus y plus z, and then a second term with the negative 2 times x plus y plus z. We distributed and created 6 terms, but then we simplified it back into 3 separate terms. Alright, so this brings up the distributive property for us, and the distributive property is written a little bit, well, more often.
AB equals A plus B equals B.
Yeah, this is what it looks like. This is abstract. So this would usually represent different numbers or terms. Sometimes they have variables in them. But this is abstract, so you could replace these with things, right? And this equals A times B plus A times C. Now we usually show these with distributive rainbows like this. And that's a double rainbow right there, which has been known to make like full-grown adults cry. It's on YouTube. You can look it up. But it's not always required that you distribute into 2 different terms. You could distribute into 1 term like this, and that would be fine, right? Still get, it's only 1 rainbow, which isn't quite as cool, but
You know what?
still very pretty. Still very pretty. Or you can, it is possible to distribute into 3 different terms, which is what we would have done in that example with the burgers, fries, and drinks. Okay, so just know that it's not always 2 terms. You could distribute into 1 or 3 or more, something like that. The next part of the lesson. So this number 21 right here, you distribute the 11 into all 3 terms. And one thing we should notice with the distribution is it's always multiplication. So when we're looking to multiply or distribute this 11 here, it's really 11 times 2x, or I would say that's 11 sets of 2x, which is 22x's. And then you also have 11 sets of, that's multiplying, 11 sets of 3y, which is positive 33y's. Now this last one, it's 11 sets of negative 8z's on this one, which would give you negative 88z's for that one, okay? This next one, the negative 5, and it may be good. I mean, depends on if you prefer, but it's not required. To show those phantom ones with the x and negative y right there. So this one is negative 5 groups of 1x, which would give you negative 5x's. But also, negative 5 groups of negative 1y's. Now it's a negative times a negative, which is a positive. Positive 5y's on that, okay? Now, of course, after you've distributed, you should look for any like terms to combine. There just isn't any in these 2 particular expressions. All right, to simplify these 2, this 23, we're going to have to distribute that as a negative 1, so that's negative 1 times 14, which is negative 14. You could say negative 1 times positive 1c, which would be a negative 1c. Of course, if you want to make that a phantom one, that's fine as well. Next up with this 6 plus 2, remember it's an order of operations, so you do need to do the multiplication first, which is distribution. So that's 2 times 1, which is 2, it's positive. And then 2 groups of 1x would be positive 2x's there. And then, yeah, we do have that 6 up in front. And then combine your like terms. 6 plus 2 is 8. And then the positive 2x, that's an unlike term, so we're just going to keep it like this. Alright guys, when you look at factoring, okay, you're looking at having to break values down into, well, we're going to use, I guess, some prime factorization, not that you have to, okay. So if you looked at different terms, let's look at something like, I think 24 is a good one, okay. You guys may have seen the factor tree like this before, but you can break 24 up into different parts. What I'm looking for are factors of 24, and you guys should know what factors are. They're values that are multiplied together to give us whatever value we're looking at, like in this case 24, right? So you'd say, what 2 numbers multiply to give us 24? A lot of people would say 2 and 12, even though you could have said 6 and 4 or 3 and 8, okay? Now 2 is a prime number, so I'm going to circle that one. And then 12 also can continue to split up between, I don't know, 2 and 6. But again, if you said 3 and 4, that's fine. So I circle the 2 again because it's prime, and then the 6 splits up into 2 and 3. And the 2 is prime, and the 3 is prime right here. So 24 could also be written as 2 times 2 times 2 times 3. And I know we've talked about this, is sometimes math is really making things look different, but without changing its value, right? And you could test that in a calculator. 2 times 2 times 2 times 3 is 24. But we would prefer to see it as its factors, 2 times 2 times 2 times 3, okay? And there is a reason for that, because when we're looking at other values that maybe have similar factors, then you can factoring it out, or just factor it out, okay? It is possible to multiply these by letters, right? Like if it was 24x, well, then you just have that multiplied by x. So it is possible to actually factor out letters as well. Now the distributive property is so pretty because it involves rainbows. But it's a method of multiplying expressions. Oh, we said that. The method we use to undo distribution is called factoring. But you guys should know what factors are from, I don't know, some other time. I don't know what grade specifically. But factoring, factors of values just tell us what numbers would multiply together to give us a specific value, okay? So when we're factoring, we're looking for maybe common factors of specific terms. You should already be familiar with factoring a number. The factors of 15 and 3 are, 15 are 3 and 5, because 3 times 5 is 15. So 25, what are the factors of 3x plus 3y? What two expressions were multiplied together to produce this expression? Well, and again, this is how this works, okay? So we would look at the factors of 3x and 3y, and there's two factors of 3x, 3 and x. And there's two factors of 3y, which is 3 and y. Now, even though right now 3 is a prime value, so we don't actually have to list the 1, because you could list 1 infinite number of times and it would just give you 3 back. So not really a big need for that, okay? And this is being added together right there. Well, what you can do is say, look at these two 3's that they have in common right there, right? Well, if you were to change this and what we call factoring this out of those two terms, then what are you left with? You're left with an x and a y, and these two expressions are equivalent. They're just written differently, okay? Now, we actually don't factor a lot other than maybe on the state test for now. However, in the future, you'll be using a little bit more. We're using, in this grade, we're usually used to multiplying or distributing the 3 instead of factoring it out for now. But there are reasons for this, which usually have to do with operations of fractions, which we've already done. And sorry, what two expressions? That's that bottom expression, 3 parentheses x plus y. All right, let's do a couple of these, okay? Let's do 26 and 27, then we'll do 20 and 29 later. So let's start with 9x minus 12 right here. Now, in order to factor this out, we need to see any common factors. And just right here, it's not quite like that last one where it's 3x plus 3y. So it wasn't, I mean, that would seem maybe pretty obvious. So we may need to factor out the 9 and also the 12 on this, okay? Or negative 12. So the 9, I'd say, what are factors of 9? Well, 3 and 3, right? So this we could show is 3 times x right there. And then 12. What are factors of 12? You could say 3 times 4. And maybe you guys have seen these factor trees before. Yeah, you could say 2 and 2 if you'd like. So this would be minus 3 times 2 times 2 right there. And from here, we're just looking for any common factors between what I have in red and purple from the 9x and the negative 12. And the only one I can identify is this 3 and this one. Okay, so again, we factor these out outside of what is now a set of parentheses, this grouping. And what was left over? Well, you had the 3x in red. There's still subtraction between. And then these 2's right here, you're going to combine those. 2 times 2 is 4. Now, if you're wondering if you can check this, you can, just by distributing the 3 back into the parentheses. And when you do, you get 9x minus 12 anyway, so that works. And that way we know we factored it correctly, but there should be some checking maybe between the 3x and the negative 4, just to make sure you have those completely factored, okay? Because sometimes students get it factored out, looks pretty, but they didn't factor it all the way. And having 3 terms isn't a big deal. But let's look at the factors of each of these, all right? So 8, I could split up into 4 and 2, and this 4, I could split it up into another set of 2's. So this is what we call prime factorization right there, because 2 is a prime number. And we figured out since 2 is the only factors of 8, and all of them are prime, it's considered the prime factorization. But don't forget the letters on that, because when we look at the analysis of this later, we're going to want to know if there's any letters in common, variables in common that we can also pull out. And then the 6, that would be like 3 and 2 right there. So that's 3 times 2 times x times y times z. And then we got plus 4a, so 4 would split up into 2 times 2. So 2 times 2 times a, and this is the prime factorization of that term. So again, we scan this and we look for any like factors or common factors between these 3 terms. And I see a 2 that's common between all 3. Now, even though there's a 2 that's common between what I have in red and green right here, it needs to be common for all of the terms, not just 2 of them or some of them. So, in fact, I can only pull out a 2 from each of the terms, okay? We got minus and plus right there. So from here, we'll just combine those. We got 2 times 2 is 4 mn. And then in purple, we got the 3, the x, the y, and z. Again, this is all multiplication. And then in green, you got the 2 and the a. So again, if I distributed that orange 2 into the parentheses, I would end up with the original expression up here at the top as 8mn minus 6xyz plus 4a. So it checks off. Again, it's equivalent. It's just shown in a different way. That's all. So for number 28, okay, now that x to the power of 2, it may be easier to see that as x times x. Okay, and then the 5x, again, that's 5 times x. And again, we are looking for any common factors between these two. And like I said, sometimes they are letters, such as this x and I guess this x. And we're looking for x's from different terms, right? Now, did it matter which x I chose from this first term, the x to the power of 2? No, it doesn't matter. I just chose the first one arbitrarily on that, okay? Now, what this means is I can pull these 2 out of both terms. But if I do that, then I'd have to show it as a distribution of this green x into the set of parentheses. Well, what was left over from the terms that we pulled this x out of? Well, you'd have this x right here, and then you'd have this 5 right here. Okay, that is factoring. Now, again, you can check factoring. You could distribute that green x back into the parentheses, and you should end up with the same exact expression that you started with, which in this case you would, x to the power of 2 plus 5x. Well, what about number 29er? Well, 4, that would split up into 2 times 2, and yeah, we still want to show the m. The 2, though, is just a, well, it's already prime on that, so we're just going to show it as 2. Well, is there any common factors between the 2 terms that we started with, 4m and positive 2? Yeah, there's this 2 here and this 2. Now, when we pull this out, though, right, because we're going to pull it out, which is what factoring is. Factoring is the inverse of distribution. Well, that first term's not too hard to see, right? That's going to be a 2m right there. And we are going to add something to it. But what do we add? Because we pulled that purple 2 out. Yeah.
That wasn't equal of 1a?
That is correct. Because, again, you could always show that as 2 times 1 if you'd like, and then you'd drop that 1. So it kind of was a phantom 1 right there. So that would be 4m plus 2 factored. And just once again, you know, if you were to distribute this 2 into the parentheses, you'd end up with the same exact expression that we started with. There's our objective. I can simplify expressions. That's the main objective. I mean, we did factoring as well. But you need to be able to combine like terms and use distribution on this assignment, okay?
Yes, sir.